To day 2 of the OpenZFS Developer Summit. We're going to have, I think, 5 shorter talks today. It's going to be a little bit more casual, so there'll be, we aren't going to, I think that Pavel is not here with his hook. So, you know, I think we're going to give the speakers a little bit of latitude if there's discussions that we want to have in terms of the time. But I asked the speakers to budget for like 10 to 20 minutes each. Let's see, no more logistics. So welcome, hopefully folks, we're using a different streaming technology to stream it to the internet today on YouTube. So hopefully that's working as well. If not, let us know in the YouTube chat there. I'll be monitoring that. With that, I'll hand it over to Serapheim. Oh, one more thing. We don't have like a microphone for the speaker. So speakers, please try to project your voices, and folks in the audience and kind of in this general area, please try to keep the background noise down so that everyone can hear them and it'll be picked up well on the live stream as well. All right, with that, Serapheim, thank you. I'm going to scoot over next to you here.
Hello, everyone. My name is Serapheim, and today I'm going to talk about the flashing algorithm and the performance results of the log Spacemap project. The log Spacemap project is something that I presented on last year's OpenZFS Summit. But at the time, the flashing algorithm was still an open question. And because of that, we didn't have any concrete performance results. So that's what this presentation is going to be about. Just to do a small recap about what the project is about. We started working on this project from a problem that we found here at Delphix. Basically, there were some pools that were experiencing degraded performance. And the reason for that was that each TXT, we were issuing a lot of IOs for metadata updates. Specifically, we were appending to each Metastab Spacemap every TXT. And the reason for that was that the fragmentation levels were very high and the workload was mostly random writes. So what we decided to do about it? Well, basically keep all the changes in memory and don't write anything to disk, right? We added 2 new range trees per Metastab, 1 for unflashed allocations and 1 for unflashed frees. And basically, how things would go would be, you want to allocate something, you would move it from the unflashed frees to the unflashed allocs. And if you want to free it, you would move it from the unflashed allocations to the unflashed frees. And now the question is, okay, wouldn't that exert a lot of memory pressure on the system? And in reality, it doesn't as much, but even in the cases that we do, we set a specific limit in the amount of memory that we have for unflashed changes. So whenever that limit is exceeded, we start flashing some metaslabs. And by flashing, I mean that the segments from these 2 new range trees that we've added for this change, we empty them out into the Metaslab Spacemap. And now the other question is, what if we crash? We have all these things in memory, right? What if we crash? How do we reconstruct that state? And the answer is that each TXT, instead of appending to each Metaslab Spacemap as we were doing before for persistence, we issue a single IO that writes all the Metaslab changes in a single pool-wide spacemap that we refer to as the log spacemap. So each TXT, we just keep all these changes in this new spacemap that we have. So in case that we crash, during import time, we just read all these spacemaps and we reconstruct the unflashed state. And now the other question is, won't that make import times after a crash take longer? You know, you do like all this reading. Well, yes, but if we control how many blocks these log spacemaps have, we also control the import time overhead that we exert at the pool. So basically, if we want to control how many log blocks we have in the log spacemaps at any given time. So solution to that is we flash a few metaslabs each TXT in order from oldest flashed to most recently flashed. And the reason that we do that is that if we flash in that order, older logs will start becoming obsolete. By obsolete, I mean that their entries would have made it to the Metaslab spacemaps, which means that we wouldn't have to read them during import time. And I'm giving an example of that just for demonstration purposes. So let's say we have a pool with like 200 metaslabs, right? We are currently at TXT 10. You know, you can see Metaslab 1 goes from blocks, let's say, from 0 to 10, Metaslab 2 from 11 to 20, so far and so forth. we written to all of them this past TXT because we're in the old state, and now we are enabling the log spacemap feature, which for now, let's say we flash one Metaslab per TXT, just for demonstration purposes. So TXT11 comes by, we write all our changes in this pool-wide log spacemap. We don't touch any of the Metaslabs so far, right? So you can see the first two blocks are freeze from blocks 3 to 4, 8 to 9, that would have gone to Metaslab 1. The rest, like 11 to 12, 15 to 18, would have gone to Metaslab 2, but we keep them all in the log spacemap. And as I said, we flash one Metaslab per TXT. So basically, by flashing, it means we're appending to that Metaslab spacemap, and you can see in gray over here, these are the obsolete entries now. So in the next TXT, we would flash Metaslab 2, and we would record all the changes of the pool in a new log spacemap, and you can see we have gray entries in both the old log spacemap and the new log spacemap because we flashed all these things in Metaslab 2. So after we do like a whole round through all the Metaslabs, let's say 200 TXTs from now, because we have 200 Metaslabs, the whole log of TXT11 is going to be obsolete. It means we don't need it anymore. Therefore, we can destroy it. So that's the idea behind like flashing in order, because we can get rid of old spacemap logs. So that's where we stopped last time. So now the question is, how many Metaslabs should we flash each TXT? The trade-offs are the following. If we flash, the less Metaslabs we flash, the less IOs we issue. But if the incoming rate of log blocks, basically the size of our incoming log spacemaps, is high, a lot of log blocks accumulate and import times take a hit. If we flash more, we get rid of log spacemaps faster, but we issue more IOs and we may end up going into this old state of the system where we're appending to each Metaslab spacemap. So as you can see, the problem is workload dependent. And ZFS needs to adapt to that. So we need to come up with a heuristic. The most naive heuristic, and the one that's the basis for all the other heuristics that you came up with, is the block limit heuristic. Specifically, we set like a limit on the amount of log blocks that we want to have at any given time in the pool. Let's say like 1,000 log blocks. So as we have more incoming blocks and log space maps, whenever we exceed that limit, we start flashing Metaslabs until we get below that limit. Basically, that limit acts as like an upper bound in the overhead of the import time that we accept. The problem with that heuristic by itself is that it's susceptible to a lot of performance pathologies. These are some sample results from a flashing simulator that I made, where you can see like there were TXTs that we were flashing basically almost all the Metaslabs in the pool. And the reason for that could be in many scenarios. It could be like our incoming rate completely changed, and we were very close to our log, but we had a lot of incoming logs on that specific TXT, and not a lot of many other cases. Basically, the problem is that the behavior is not consistent and not predictable. We can't reason about it. And because I don't have time, this is a lightning talk. There are a bunch of other heuristics. I've open sourced my simulator, and you can give them a try. You can specify different parameters, try your own, things like that. And I want to talk about the ideal heuristic. The ideal heuristic would take into consideration the distance between the amount of log blocks that we currently have and the limit that we set. So if we are far away from the limit, you can say like, okay, we are still good. We don't need to flash as much. If we are close to the limit, we can say, oh, the system is under pressure. Maybe we want to flash a little bit more. The second consideration is the current incoming rate. Regardless of how far you are from the limit, if your incoming rate is high, it means that you're going to approach it like very quickly. So you need to take that into consideration. The third thing is the distributions of Metaslab flashed over our log spacemap history. Have we been flashing a lot? Have we been flashing little? That's important because basically our flashing history correlates to how easily we can destroy old log spacemaps. And finally, the distribution of log blocks over our log spacemap history. How has the incoming rate been in the past few TXTs? So with this in mind, we came up with the running sums heuristic. Basically, the way that this works is that each TXT we take the current incoming rate and we project it in the future.
right? We kind of like make projections on what we are getting so far. And we're saying like, okay, in some TXGs from now, whenever the limit is exceeded, how many metaslabs would we need to flash to stay below the limit? And then we take the average of these metaslabs over the TXGs that we projected. So we can tell, okay, if I start flashing from now, will I stay below that limit? How many metaslabs do I need to flash from now in order to stay below that limit on that TXG? So here's an example that I have. You can see that that table is basically I'll explain all of this. This is the history of our log. Each row, it's a log space map. So the first row is the log space map of TXG10. It has 2 blocks. I'm going to talk about the running sums in a bit. And at that TXG, we flashed 1 metaslab. At TXG11, we had 6 incoming blocks, and we flashed 2 metaslabs. So the idea of this whole table and the running sums is at any point in time to say, if I wanted to get rid of 8 blocks, how many metaslabs should I need? How many logs do I need to destroy? And how many metaslabs do I need to flash in order to destroy these logs? So for example, if I just wanted to get rid of the first log, I would flash 1 metaslab, which gets rid of 2 blocks. If I flash 3 metaslabs, it would get rid of these logs, log 10 and 11, and it would flash 8 blocks. You get the idea, and that's why we call them the running sums, basically. So the scenario for this example is that we are currently at TXG16. There's no log over here for TXG16. We have 24 log space maps. You can see it on the running sum right here too. And we set the block limit of 32 blocks. And for now, just for demonstration purposes, we say that we have 4 incoming log space map blocks. So we start running our heuristic. In 1 TXG from now, the limit is 32, and we currently have 24 blocks in our pool, and the incoming rate is 4. So in 1 TXG from now, we would end up with 4 blocks below the limit. The limit is not exceeded, there's nothing to do. In 2 TXGs from now, we were left with 4 log blocks below the limit. As I said, we project the incoming rate, so we get exactly to the limit in 2 TXGs from now. Now, in 3 TXGs from now, with the same incoming rate, we exceed the limit, right? So we want to start flashing. So in order to get below the limit, we need to free at least 4 blocks, right? Exactly how much we exceeded. So the first row in the table with a block running sum that's at least 4 blocks is row 2, that's TXG11. So we need to get rid of TXGs10 and TXGs11 logs, which requires flashing 3 metaslabs. And that would release 8 blocks that would get us below the limit. So we need to flash 3 metaslabs in 3 TXGs in the future. So 3 over 3 is like 1 metaslab flashed per TXG. And we can go on. We went below the limit by 4. The incoming rate again was 4, so the limit was not exceeded. Then we exceeded the limit again, and based on our updated table, we say, okay, now we need to flash 7 metaslabs to release 6 blocks because we exceeded the limit by 4. So 7 over 5 TXG is going to be, we need to flash 2 metaslabs per TXG in order to stay below the limit. And we keep going until we go over our whole table. And by the end, we just take that column and we take the maximum of the metaslabs flashed per TXG that we calculated in the past, which guarantees us that we're going to stay below the limit based on the incoming rate of blocks. So here's some sample simulation results. This is from a hypothetical pool of 300 metaslabs, and I set the block limit to be 300 blocks. And the incoming rate was like randomly chosen between like 10 and 64 block blocks each TXG. And the results were that we were flashing 11 metaslabs on average each TXG. And the maximum that we ever got to was 24 metaslabs, which is like 8% of the metaslabs in the pool, which is pretty good in terms of IOs. So yeah, a small optimization that we did, because the table can get very big depending on what your block limit is that we decided to keep a summary in memory all the time of the log spacemap table, which decreases the running time of the heuristic. Doing this, implementing this on my simulator yields similar results with the actual algorithm. So yeah, I've been talking about this block limit that I arbitrarily set. and we want to come up with a same default because this limit indirectly controls the flashing rate. So the higher the limit, the less metaslabs that we need to flash. The lower the limit, the more pressure on the system will need to flash more. So the driving factor on deciding on that was that we want each flash to count, meaning we want every time that we send an I/O to append to a metaslab, we want the block size to be utilized. So in theory, if we want to get rid of the whole log, basically flash all the metaslab spacemap, we would want each metaslab to end up with at least one more block in its metaslab spacemap. So the question here is like, what's the correlation between log entries and Metaslab spacemap entries? So we looked into that. Log spacemap entries, as I said, may have obsolete entries. And the fashion that they work most of the time is about half of the log spacemap entries are obsolete. As you can see, the oldest log has all its data flashed, and the newest log is mostly consists of unflashed data. And everything in between is like kind of like an intermediate state in an increasing rate function. So we could make the assumption that at any given time, about half the log consists of obsolete entries. The other thing to take into consideration is that Metaslab spacemap entries are more generally one word, while log spacemap entries are always two word. And the reason is because we're talking about a pool-wide spacemap. We need two log entries because there's a field about the VDEV, so we can be specific which metaslab on which VDEV we're talking about. So far, we could say that our factor of log entries to Metaslab spacemap entries is around 4. And if that's not enough, well, there's also consolidation in the log spacemap. For example, you may have a block that you allocated, freed, and then allocated again. But in the Metaslab spacemap, it would count as only one entry, as like one block allocated. So the consolidation comes into play. So we decided to make that limit a tunable factor in terms of number of metaslabs in the pool. And we decided to make that tunable a 4 just to be conservative. So now performance results. This is the number of IOPS over 5 days, a 5-day long experiment that we ran. Basically, what we did is we had 2 pools with the same setup, but one of them had the log spacemap feature enabled. And we started doing random writes to them until they reached high fragmentation. And they also reached a steady state in terms of number of IOPS. Basically, there weren't any fluctuation. Everything was steady. So looking at the last 10 hours of this, we see that the log spacemap enabled pool showed a 40% win over stock bits. And that was, at that point in time, pools had reached around like 91% fragmentation. And the one with the log spacemap was doing like 240 IOPS more consistently. Also, during the course of these experiments, we verified our assumption about the amount of obsolete entries in the log spacemap at any given time. So basically what you need to emphasize more is this ratio over here, which is around like 0.5 at any given time, which means that we can verify our assumption about half the entries being obsolete at any given time. There are a lot more to this project. I wrote a blog post about it. There's also my talk from last year and a lot of other stuff if you are interested in Spacemap or like how ZFS does allocation. And questions?
In a workload like that where you have so much fragmentation, would having fewer metaslabs improve things?
Yes, we changed. Part of this change was also changing how the number of metaslabs per VDEV are assigned. So we made some changes for each metaslab to be like a certain, I don't remember if it's like 8 GB, something like that. But basically, yes, with this change, there are also pools will have less metaslabs in general.
Right, I was wondering about that.
Yeah.
To make a higher level point, just so the I think in your previous talk where you talked about the motivation of the whole project, we talked about the fact that, yeah, like if you didn't have this,
Yes.
lowering the number of metaslabs would kind of achieve the same thing because you're only appending to a smaller number of metaslabs rather than 200 per VDEV or whatever. But that has a lot of other trade-offs, like memory usage, the metaslab load time, which are all kind of like basically like the previous before Serapheim stuff. You were kind of screwed on every dimension. Like load times were bad, memory usage was bad, number of IOPS was bad, and like yeah, you could trade off between any of those, but you're just going to make another one of them or two of them like much even worse, and they're already bad. So this lets us give much more flexibility, and the system is much less sensitive to the number of metaslabs, so total number of metaslabs. So in some cases, we're able to increase the number of metaslabs while still improving performance because we aren't writing to all of them. So you have more metaslabs, so you have like less memory used, shorter metaslab load times. You can also have larger metaslab block size, which decreases the load times. These are all changes that Serapheim made with this work.
Yeah, actually, I talk about these trade-offs on my first talk. It's just I wanted to run on this slide talk for the 20-minute.
I'm mostly thinking about what Matt and I talked about at the ZFS User Summit of now that we're getting really, really large hard drives, like 14 terabytes, that if you do a 12.5 RAID Z2, your metaslab might be getting too big.
Yeah.
And maybe instead of magically deciding there are 200 metaslabs, suitables of like the minimum and maximum size of metaslabs, and then we kind of
That's exactly what you did.
pick the
Yeah,
number
yeah.
and-
So basically, we did what we ended up doing is that so for pools that are very small and pools that are very large, we set up some like limits in the number of metaslabs. But in between, we basically have like a fixed metaslab size. And we basically put more metaslabs as your storage capacity grows.
Is the log always a good idea, or do you want to kick it in when a pool reaches a certain level of fragmentation?
So that's a good question. I haven't done like a lot of testing in terms of that, but so far because we run with this feature enabled so far since like February, and we haven't found any issues with it. The thing is that if you don't have a lot of fragmentation, you're still dependent on the incoming rate. Like basically the flashing algorithm doesn't work in terms of fragmentation, right? So that ideally shouldn't matter.
So with your testing, you kind of were doing a pool that was doing a lot of churn.
Mhm.
Did you do any testing where you did like ZFS destroys and like had a huge influx of freeze? Or how would that impact kind of like your algorithm for keeping track of like the running table, running sums?
Yeah, I think that's the case too, because at that point you'd have a lot of freeze, right? And assuming the same workload, the freeze would be scattered around all the metaslabs, right?
True. Yeah, but I guess the difference would be like with a normal churning pool, your incoming rate is, might be somewhat constant.
Mhm. Also, you're saying if there was a bump.
Then there's a huge influx.
Yes. Actually, that's exactly what made that first block limit heuristic go crazy. And we tried with a lot of different like incoming trends. So, for example, if you suddenly have like something steady and then you jump, or you go very low, or have something like that looks like a sign that you kind of like have a lot of incoming rate, then it goes down, and also like a randomized sign. So even though it's not like exactly still like a perfect sign, it's like randomized, things like that. And sometimes you receive like random fluctuation like this. So yes, indeed, I did test the flashing algorithm with that, and it showed normal results.
So it looks like you did some sort of control systems like PID controller for the flush algorithm to like make an accumulator and then look at the rate of change. So that's why it kind of
it's very interesting because like we spent a lot of time on this, and I started reading like on queuing theory, and I couldn't find any model that has this weird correlation between like these two different distinct things, like having a relation. In our case, the metaslabs flash and the log blocks that we can destroy. So yeah, that's what we come up with.
I'm always interested in on-disk format changes. The log itself is stored in a new pool-wide object, which is presumably referenced in the MOS.
Yeah.
Is it a new DMU type, or is it's these two word-wide things now? It's not quite the same thing, is it?
I'm not exactly sure if I understand the question. The way that we store it, you're right. We store it in the MOS. There's a
Right.
zap.
Okay,
I think inside the MOS, it's a
Right.
zap, and we basically have like the key is the TXT and the value.
oh, okay,
Is the-
I was curious what exactly was stored.
Yeah, yeah.
And since it's stored in the pool itself,
Mhm.
appending entries to it requires Metastab operations. So there's kind of a feedback going on.
Yeah,
around it,
but
right?
yeah.
Did you investigate storing it in maybe the ZIL or something like that, which is
Uh,
pre-allocated?
I
Would that
actually
be possible? I don't know.
I think you're talking about sync to convergence.
Okay.
Yeah.
So like the before Seraphim's changes, there's this idea of sync to convergence where like you might be syncing and then you have to allocate some stuff
Right.
and then you have to write out the space maps. So we actually, and you still have that with Seraphim's changes,
Right.
but because now you're only writing one space map. Like you can, like in the worst case, one more sync pass means that you're appending to one space map.
Sure.
We actually saw the number of passes required to sync to convergence go from like dozens to like 4.
Yeah.
And it's very consistent. It's much more consistent with Seraphim's changes than before.
So it can be a pretty big performance gain.
Yeah.
In that case.
So there's a lot of like collateral wins from this one change.
That's actually very interesting because I had always wondered sometimes how many passes were required. Since I don't think that's one of the few things for which there isn't an easily available statistic. Really.
Cool. Thanks
everyone.
Thanks.